So we could think of the impulse response as evidence that something occurred, something happened, an event happened. And in real life, nothing can really move instantaneously from one position to another position without taking some time. So usually when an event occurs, it has something that we call an envelope on it. Maybe it has an attack time, the time it took to get to this new position. If the force is continuously applied, there might be some sustain, and then when it's removed, then it takes a little bit of time to relax back to its original. If you have a recording of an audio signal, is there a way to extract that apples and envelope out of it? So I'm going to answer that question in a minute. So this is the riddle of the arithmetic operator. When I join with you, when I join you with nothing, there is nothing but air. When I join you with one, you're the only one there. With one, I disappear. With zero, you disappear. What else? It's a multiplication. Because, well, let's see, I'll go back to it. If you put, if you replace this question mark of times, then u times 1 is u, so the 1 kind of disappears, and u times 0 is 0. So when it comes to audio, multiplication is almost like this miracle operator. You can do all kinds of things with it. If you want an attenuator, you can just multiply by a constant or a control. That when you control is 0, you get 0. When you control 1, you get the signal straight through. If you want to impose an amplitude envelope on a shape, you just can multiply your signal by that shape, by that envelope, and you impose the amplitude envelope on it. And if you want to create a more complex spectrum, take two signals and multiply them together, and you'll get all kinds of sums and difference frequencies. That, and Pete Johnston is going to be talking more about that tomorrow. So what happens if you multiply two sine wave oscillators by each other? So I have one sine wave that's 1,000 hertz sine wave and another one that is adjustable. So right now it's 400 hertz. And this is a spectrum. So you have two simple things, but when you multiply them together, you get a different spectrum out. You get the sum of those two frequencies and the difference of those two frequencies. So if I put something like 2 there, now you hear the amplitude changing. And as I increase it, now you hear two different frequencies diverging. But I think Pete's going to cover that tomorrow in his talk on ring modulation. So that also works for impulse responses. If you multiply the impulse response of a low-pass filter by a sinusoid, it will make a bandpass filter centered at that frequency of the oscillator. So you can move impulse responses around too. So here's the impulse response of a low-pass filter, and this is the frequency of the oscillator that I'm multiplying by. So the thing on the right looks just like what we saw in the first section, the response to a bandpass filter. And just to test that that's really true, I fed that into the response input of the cross filter and put noise to it just to prove that that's true. So it made bandpass filter. So that was just taking a low-pass filter response, multiplying it by a sine wave of a certain frequency. So now, just as an interesting case, what happens if you multiply a sine wave by another sine wave of exactly the same frequency? What would be the sum of the difference frequencies in that case? If they're both, say they're both 1,000 hertz.
You get 2,000.
2,000 zero.
Yeah. So the interesting thing about that is it's zero. You can see over here, well, this is 2,000, and then this is something, a component in DC.
Mm-hmm.
So you have, in a way, you've got amplitude here, right? I mean, the DC has some amplitude, but there's no frequency. So in a way, you've gotten the amplitude of your signal without the frequency bit. So if you take a mystery amplitude, this is a sine wave that has some unknown amplitude envelope on it, and I'm going to multiply it by itself. Then I'm going to put it through a low-pass filter to get rid of the thing that was an octave above, like 2,000. And then I'm going to look, use info to look at the full waveform. And that was only the DC. That's the DC part. But it was, but you can see the envelope shape because it gave you just the amplitude without the frequency. But that's actually how people extract the envelope. That's one technique for extracting the envelope. That's called root mean square. Because you square the signal, then you take the square root, and then you take the average. The averaging is the low pass part. So in a way, the amplitude envelope doesn't really exist. Really, all you have is the signal. And I had a psychoacoustics professor who said the frequency doesn't exist either. So really, this is all you have. You just have these instantaneous changes in the waveform. But somehow, obviously, somehow we interpret that as having an amplitude envelope and the frequency. But it must happen here. It's not just out in the signal itself. And that would have some kind of a survival value, I think, too. That if you identify a frequency that sounds like a car engine, and then you're identifying that the amplitude of that car engine is getting louder at a rapid pace, you're going to jump out of the way. But what's the difference between what we would call a signal and what we would call amplitude envelope? Because they're both amplitudes. Well, generally, the signal has both positive and negative deviations of pressure, and whereas the amplitude envelope is just the magnitude of that. And also, the envelope has doesn't have all that fine structure. So most of the algorithms for extracting the envelope do those two things. They get rid of the fine structure and they make it all positive. And these are some Kyma modules that you can use for extracting the amplitude envelope. Most of them, to get rid of negative values, they'll either square it, because that'll get rid of it, or maybe take the absolute value. This is a drum. Oh, sorry, I have to do the switch. Okay, there's the root mean square. And I'm going to go here and test for the full waveform. I'm going to have to wait 7 seconds for that to play. And that's the extracted envelope. Once we have the envelope, how could we apply that to a different signal?
Multiply?
Multiply, the miracle operation. So here's it's called product, and there's that same root mean square amplitude follower of the drum, and here's an orchestral sample, and it will multiply them. You apply that to that signal.
We've got to do this.
This is a related one called peak detector. With the peak detector, you have control over how it responds to changes in the positive direction, that's the attack time, and how quickly it responds to changes that go down in value as release time. And it's being multiplied by a recording of And the reason you can see that, just as an aside, is I put the peak detector into a sound global controller, and that will change the signal or amplified expression into a fader and control it for you. So it will bounce by itself without you having to control it. So we extracted some amplitude envelopes. How could we extract a frequency envelope as a signal? One technique is called autocorrelation, and all it is taking a waveform, take a waveform, and make a copy of the waveform, and initially have them lining up on top of each other, and they gradually shift one of them relative to the other one, and compare and see when they seem to line up again. And whenever they line up again, that distance is probably the period of repetition, because after you get to one full period, then they'll line up again, and this time they're canceling out. And so it's actually just the same thing. It's multiplying again. The way that autocorrelation works is you take the two signals and you multiply them. But instead of, you also, in this case, will add up all the values and compare to see when they are correlated. You will have high values. When they are completely uncorrelated, it will be 0 because they're out of phase in multiply. So This is a 1,000 hertz oscillator multiplied by itself. And just to show. Thank you. So I'm going to control using the Wacom pen. I'm just going to change the phase of one relative to the other. And you see what happens when you multiply them together. And you see how the correlation goes down at one phase, and then if I go far enough, there's a negative correlation, and now it's going positive again. So that's the inner workings of how the pitch detector works. So the module is called Frequency Tracker.
MS done.
Okay, and that's feeding into Frequency Tracker. And then I put the Frequency Tracker into the frequency field of this morph to the Kyma sound. The output of any Kyma sound is between -1 and 1. So to put it into a range of frequency, I am multiplying by signal processor half sampling. So that just did extracted the frequency envelope out of the pitch, out of the singing, and put it onto a different synthesis. And just as a funny thing, but also a useful thing, when you extract the frequency envelope, you can feed it into a frequency scaler, which is like a pitch shifter. And if you take the inverse of the envelope that you're extracting, you can remove all the melody out of your voice. Because whenever your voice goes up, it's going to divide, so it brings it back down.
No matter what I sing, it comes out monotone.
In addition to tracking, following the frequency envelope, you can also set up something to detect when a particular frequency occurs. And this is kind of like setting out some resonant objects like glasses of wine and asking an operatic soprano to sing the highest pitch that she can sing. And then you see which of the glasses breaks. And you would know which frequency she hit. And you can do that with the module that's called Energy at Frequency. So I use a replicator to make 12 of those. And I'm detecting from 54 NN plus 12 half steps. So those are just resonators, those are just like wine glasses sitting out there at every half step. And then when you hit that frequency, then this fader will go up. And then I'm using that fader to control the amplitude of the oscillator. Here's some more Capitol. As the generated event, I am calling it A, exclamation point A, but then I want each one to be independent or labeled. So using this tag suffix 2, and then say 54, which was the bass pitch, plus voice number. So each voice number will be resonating, will be sitting there looking for a different half step. If you add frequency detector gate, if you use that prototype, you could turn it into a trigger event rather than a continuous amplitude input. So I'm using that to trigger the function generator that's feeding into a harmonic resonator. But same idea. So if you want, for example, you could use that in a timeline, that when the signal hits a particular pitch, it could break through a wait until in the timeline. You could use that for control signals. By extracting these features, it's like extracting the features from the environment and using, it opens up the door to using audio signals as controllers. So going beyond having faders and other kinds of controllers, to actually using your voice or an instrument or the environment itself that Scott Miller uses to as controllers for the audio signals that you have. So another, besides extracting amplitude and frequency, we're pretty good at extracting some kind of, if you want to call it timbre, something about the spectrum. If you think of the almost a spectral envelope or shape or like a stamp. So imagine that you have an EQ on your music playback device. You probably have some kind of an EQ setting where you can boost or attenuate different frequencies. So imagine that at of each of those bands, you had an amplitude problem. Then you could have some kind of a readout of how much energy was in each of those bands. And that's the idea behind vocal. So here's the bracket EQ. So you hear some speech, you hear different bands of speech. Now I'm going to put one of those RMS squares on the output of one band. Okay, well, here's some more effects. Okay? I have here voice number EQ2. So with the second voice, will put a 1 in the 500 hertz band, and it will put 0 in all the other bands. So that was just a way of making a whole bunch of single band pass filters. And I extracted the envelope out of each one of those bands and multiply that envelope by noise coming through the exact same band. Okay, so we're getting a little bit of the rhythm of the speech, but And this is the vocoder module. And this vocoder has 66 bands. And I have the same speech source and noise coming into it. So now you can start to actually hear the speech. This is a combination of noise with an oscillator on kind of a global pulse waveform and a speech sample with a 72 band vocoder.
I am the cephalophage. Open your mind and surrender to me. I will ingest your knowledge, leaving an empty synaptic shell.
This is only the oscillator.
I am the cephalophage. Open your mind and surrender to me. I will ingest your knowledge, leaving an empty synaptic shell. Resistance is pointless. I am the cephalophage.
So that's what's happening with the vocoder. You have the kind of like an analysis. You have this bank of filters and some voice coming into it, and it extracts amplitude envelopes coming out of each one of those bands, and then multiplies by parallel bank of filters, bandpass filters, with a different input into those filters, usually noise or something pretty broad. So the vocoder is tracking the amplitude envelope in each band. What if you could track both the amplitude envelope and frequency deviation in each band? That's the idea behind doing this spectral analysis. So you would, to resynthesize after you have all those envelopes, you would get a bank of oscillators. You would multiply each of those oscillators by its amplitude envelope and change the frequency according to the frequency deviation envelope. Each one of the sine waves obviously has got a super simple spectrum, but when you add them together, you recreate a complex spectrum. The GA synthesis that you see in Kyma is group additive synthesis. And that is an optimization of the complete additive synthesis. That's when you look at the spectrum, and instead of using the simple sine waves in each oscillator and using hundreds of oscillators, maybe you could reduce it down to 5 oscillators and just have a more complex signal inside each one, a more complex waveform inside each one. Exactly. So here is, first of all, this is not my voice, this is 128 sine wave oscillators following the amplitude and frequency envelopes for each band of the analysis. This is an additive resynthesis of a piano tone using the oscillator. Just to look at the DC status. So the additive synthesis can use a lot of horsepower, especially when you give it lithium. This is the GA synthesis. and it has actually more voices and uses a lot less DSP power. You do lose some detail doing that, but for some applications it might be okay, and it uses a lot less DSP power. That was just to show you the name that one is Morph 2D Kyma GA.
Yeah, more, you could just morph in the time. You gotta start and stop them.
Yeah, that's a good question.
Yeah.
Actually, the morph in that was only in pitch space. So it was.
So you're interpolating between like a sample at a low point and a higher one, and then creating morphs to synthesize.
Exactly. Yeah, there were only a few originals, and you morphed it in between frequencies. So in order to kind of maximize the combinations and the recombinations that you can make in Kyma, the spectral sources and the generators, the banks of sound generators, are two separate modules. So basically you can pick one from column A and one from column B, and you get 24 different sequences algorithms right there. Okay, so the other reason for splitting them up is that you can do some signal processing on the spectral source before you synthesize. But in order to do that, you just have to bear in mind that the format of the spectral source. So it isn't really, you can listen to that signal if you want to, but it's not a very pleasant sound. You probably have accidentally played them sometimes. And yeah, so the output isn't intended to be listened to. It is a stream of amplitude envelopes and frequency envelopes for one of the banks of generators. And this format is, let's, for a simple example, say that you have 8 partials. That would be a frame length of 8 samples long. And on the first sample, on the left channel, you would get the first partial's amplitude. On the right channel, you would get the first partial's frequency. Second sample, you would get the second partial's amplitude, the second partial's frequency, and so on, until you got to the 8th one, and then it would repeat, where you start a new frame. So this, let's say these are the amplitudes. It's got a kind of an exponential decay because the fundamental is louder. It's basically a sawtooth. So each partial has one over the partial number as example. And then these frequencies are just increasing. This is the fundamental, the lowest one, and it's just increasing up until the highest partial. And then it starts over again. So I have this set up to actually look at that. Here's a synthetic spectrum from array. The synthetic spectrum from array, you actually give it an array of amplitudes and an array of frequencies, whatever you want. And this is I used a shortcut here, which was to use small pup to make the array. So I didn't want to type in 500. So the shortcut is 1 to 512 collect. That's going to make a new array. That's a big array. And for each time through this loop is going to set I to a different number, 1 through 512, and multiply by this 43 hertz. So if you ever want to look at the result, you can just select and go to info. edit, evaluate, or as I always use the key combination of Control Y, where you evaluate it. And then you see why I didn't want to type it. So this is what that spectrum looks like. That's the left channel with the amplitudes, and this is the right channel with the frequencies. And that's the waveform that comes out as a kind of a sawtooth shape, or band limited sawtooth. So the different ways of making a spectrum. This is the live spectral analysis. You could put a live signal into there, and it will do the analysis here, and it feeds into an oscillator bank. And that's how you could do the live analysis resynthesis. The next thing on the list was spectrum and RAM, which is looking at a pre-analyzed spectrum, and put just the neighboring file and play it with but as Ed was pointing out earlier, you could change the frequency without changing the timing, and vice versa, you can change the timing. Without changing the frequency. And this is the synthetic spectrum from array, which you could also feed into an oscillator bank. But in this case, I just made it so it generated all of these buttons so that you can control which harmonic was played by pressing one of those buttons.
And before that, what was stretched?
Oh, the time index was stretched. I'll show you how to do that. So the spectrum in RAM has an input called time index. And ordinarily, time index would go from -1 to 1, -1 being the beginning of the spectrum recording, and 0 in the middle, and 1 is at the end. And it's actually using the function generator to generate that time index.
You got anything?
Yes.
يا فاطمة مولات العين يا فاطمة يا فاطمة مولات العين 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 يا فاطمة مولات العين.
Another one of the spectrum makers or spectrum sources is spectrum from single cycle. This one you can specify a waveform, and it will give you the spectrum of that waveform. And that could be helpful if you say you have an analog synth that you want to capture one cycle from that. And you can get the spectrum of it and then use it to control an oscillator bank. This was just from a Julian pipes, just one cycle clipped out of a Julian pipe. waveform, and you can, it's also the spectral resynthesis is band limited, so you can resynthesize these waveforms without aliasing them. Because maybe if you're playing them up higher, it will automatically not generate the sine waves that are out of range of the alias. Because of the fact that the spectrum source is actually a signal, you can use other sounds to make the left channel and the right channel. So with the synthetic spectrum from sounds, you feed in a sound that will be your amplitude source, and you feed in another sound that is your frequency source. So for the amplitudes, I have this reverse exponential, and I put it in an oscillator where the repetition rate of the oscillator is the frame rate. So I just wrote in here I wanted to generate 512 partials, so I put 512 samples. That's going to be the duration of one frame, and I said take the inverse of that, and that will be the repetition rate. That will be the frequency of the oscillator. And for the frequencies, I just use an oscillator on a ramp, and I put the same thing, 512 samples inverse. Let's see how they wait for that. This I thought was more interesting. Instead of having just the round for the frequencies, I used this waveform just to use a more interesting waveform. So now this is the a picture of, it would be like the spectrum, except these are the frequencies. So you can maybe just play whatever spectrum you like. And the last one that I'll show is the spectral shape. With this one, you supply a wavetable that is going to be interpreted as a spectral envelope, or just the shape of the spectrum. But I set it up so that I could draw that shape using this memory writer. So I'm using a Zen oscillator where each of the Y values is coming from the Wacom tablet. And I'm writing that waveform into the memory writer, and then that waveform is being used as a spectral shape. So you can, that's just to give an idea of all of combining different things together. It makes this magical sound. Yeah, they're very special. Okay, so just conclude this section, I wanted to show that you can combine with different generator banks as well. For example, this is using the oscillator bank.
Did you ever have a feeling that you wanted to go and still have a feeling that you wanted to stay?
In this case, I'm using the continuum to control the frequency of playback and the rate of playback. Front to back is controlling the rate, and the frequency is the pitch of the continuum.
Did you ever have a feeling?
But you can do the same thing with that same spectrum and control a bank of filters.
Did you ever have a feeling that you wanted to go?
In that case, I put the bandwidth of the filters on the front back of the continuum.
Did you ever have a feeling that you wanted to go?
There's another bank that's called the formant oscillator bank, and that lets you control the apparent formant without changing the fundamental frequency. So you could get that chipmunk and the monster.
Did you ever have a feeling that you wanted to go and still wanted to stay?
Or you could use a cloud bank, and that takes, for every one of the partials has a gray cloud. And so the center frequency of the gray cloud is the frequency envelope of the spectrum.
Did you ever have a feeling that you wanted to go and still have a feeling?
I was just changing some of the green parameters. So one more thing before the break, I wanted to play mystery resynthesis. That's using a harmonic, or it's using a cloud bank. Let's see if we can identify our source.
THX.
Oh, close, but
There's brass in there, isn't
The sound of music.
Okay, take a break, and when we come back, I can either continue and finish this against the morphing, or we can skip to doing spatialization.